Hello, my name is Egor, and I would like to present the paper Fine-Grained Classification of Subquadratic Patterns for Subgraph Listing and Friends. In this paper, we give optimal algorithms and matching conditional lower bounds for minimum weight, enumeration, and listing subgraph isomorphism problems for pattern graphs for which this optimal time complexity is truly subquadratic in terms of the size of the input graph. Let's dive right in and start by giving an intuitive example of what the problem asks for. In the problem of H subgraph isomorphism, we're given a host graph G as input, and also we have a constant sized pattern H that we would like to find in the host graph. Something like where is Waldo gain? Here it is, for example. It's a meta problem, so for each fixed pattern H, we have a different problem. It is one of the fundamental problems in theoretical computer science that has many applications. For example, it captures well the notion of multiple join queries in database systems. The problem has many different variants. We may want to search for an induced subgraph or not induced. So for example, do we want to find exactly a dog, or a dog with a party hat would also work. Next, there is a colored and not colored version. Are all vertices of the host graph indistinguishable, or do we have some parts and we want to choose one vertex from each part? And finally, there are many operations, many options of what exactly we want to find. Do we just want to decide whether there is such a pattern or not? Do we want to count them all? Maybe we have some weights on edges and we want to find an extreme pattern that minimizes or maximizes the sum of its edge weights. Or if we go back to the database motivation, and maybe we want to output all copies of the pattern H in G. This would be called a listing version. And enumeration is when we want an algorithm that outputs these copies back to us one by one. We will focus on the version of the problem where we want to find a non-induced colored subgraph, and we'll solve the problem for the last three versions. Our algorithms will work for the first two options too, but for them, our lower bounds would fail, as sometimes fast matrix multiplication gives an improvement for this version of the problem. In this talk, I will focus on the minimum weight version of the problem, as it will be the easiest to explain, but all the results from this talk work for the enumeration and listing versions in the same way. So let me finally define the problem that we'll focus on. For a fixed pattern graph H, the problem of minimum weight colored H subgraph isomorphism asks, given an edge-weighted host graph G with parts labeled with vertices of H, to find an edge subgraph of G that is isomorphic to H with the sum of edge weights minimized. For example, in this case, H is a triangle, so G has three parts, and we need to choose one vertex from each part so that they form a triangle and the sum of its edge weight is as small as possible. Here we should take these three vertices, which form a triangle, of total cost 7 plus 3 plus 2, so 12. And it is indeed the cheapest triangle in this graph. But we do not focus on the minimum weight triangle specifically. We want to look at this problem through the fine-grained complexity lens. So ideally, for all patterns H, we would like to find an optimal algorithm and a matching conditional lower bound. But this would probably be too ambitious, as this is a big open problem in parameterized complexity theory. As shown by Marx, the current best upper bound exponents are proportional to the tree width of the graph. But the lower bound exponents are not only not equal to them, the gap is actually unbounded in general, and it's proportional to the logarithm of this exponent. So, as finding the exact time complexities of all patterns when this time complexity is high does not seem tangible, it's only natural to focus on patterns of low time complexity. In particular, we'll focus on patterns for which the problem can be solved in truly subquadratic time, in terms of the number of edges in this graph that we denote by m. There is some prior work in this direction. For example, it's known that if a pattern graph H is a tree, the problem can be solved in linear time. Alan Juster and Zwick in 1997 used a high degree, low degree approach to give some subquadratic algorithms for cycles. Jogli, Karen, Ray in 2015 showed that some larger family of patterns that we will call calligraphic P admits truly subquadratic algorithms. Though this family is not complete and the algorithms they present are not always optimal, just subquadratic, this family will be important stepping stone for our results, and I will later define what this family calligraphic P is. Also, they showed that one specific graph depicted here does not admit truly subquadratic algorithms under some fine-grained complexity assumption. More recently, Van Curtis et al. Developed the same lower bound setup that we use and applied it to prove optimality of these algorithms for cycles. They also designed optimal subquadratic algorithms and matching lower bounds for bipartite cliques with exactly 2 vertices in one part. So there are a bunch of these results giving subquadratic algorithms. Sometimes they're optimal, sometimes they're not, but still, to the best of our knowledge, no complete characterization of all patterns for any exponent above 1 was known in any prior work. So only the linear time complexity is well understood. And now, moving to our results, we consider the family of patterns that do not contain any of these 3 graphs as induced minors. So this is a K4 clique. This is exactly the graph for which Jogli, Karen, Ray proved a quadratic lower bound. And this is another pattern that we introduce. So it's common to describe families of graphs in terms of forbidden minors, and we do something similar, but with forbidden induced minors. We show that all patterns in this family admit truly subquadratic algorithms, and this family contains all these smaller families that were analyzed before. This is clearly a pretty obscure family of patterns, and it would not deserve so much attention if not for the following fact. For all patterns outside of this family, we prove quadratic lower bounds. So this family turns out to be exactly the family of all patterns that admit truly subquadratic algorithms. In other words, these are exactly the 3 reasons why a pattern could be hard. Because it contains this induced minor on this, or this induced minor. What is actually even more surprising is that we not only develop these subquadratic algorithms for these patterns, but we showed that they are optimal. So we have a matching fine-grained lower bound for each and single one of the patterns H from this family. And as you will see later, this time complexity is very complicated. So I find it really surprising that such a result is even possible. This description of the family in terms of induced minors is very concise, but not constructive. So to be able to read off the time complexity from a pattern, we will formulate an equivalent definition of this family. As I already said, the main stepping stone in this direction will be exactly this class calligraphic P that we will now define. To do that, let me first introduce something that we call a parallel path graph. A P, L1, and L2, and so on Lk is a graph that consists of 2 specified vertices and a collection of k disjoint paths between them of lengths L1, L2, and so on Lk respectively. For example, this is P664132 because there is a path of length 6, another path of length 6, 4, 1, 3, and 2. And now we can define the family calligraphic P. It contains of a single edge, so P of 1, a triangle, P of 2, 1, and all the P graphs where all paths have length at least 2, and at most 2 of these paths have length strictly larger than 2. In other words, these are graphs p alpha beta 2 to 2 and so on 2, repeated gamma times, which we denote as p alpha beta gamma times 2 for short. Here are some examples of these graphs. As I already said, an edge suits us. Any cycle is in calligraphic P, as it's either a triangle or p alpha beta gamma times 2 for gamma equals 0. A graph where all paths have length 2 also works. In this case, you can see that it's actually a bipartite clique with 2 vertices in one part, something that was also analyzed in previous work, as I said before. Furthermore, we may have one long path and a bunch of paths of length 2, or we may have 2 long paths and a bunch of paths of length 2. On the other hand, this pattern would not work, as it has a path of length 1 and we only allow paths of length at least 2. This pattern would also not work, as it has 3 long paths and we only allow at most 2 long paths. And finally, this pattern would also not work, as 2 of its paths intersect each other and we only allow disjoint paths. As I said, this family is an important stepping stone, and now we're ready to define the whole family of subquadratic patterns, which is actually pretty quite simple. We define a family calligraphic P+, such that H is in calligraphic P+, if and only if it can be obtained by repeatedly stitching patterns from calligraphic P by vertices and edges. Let me give you an example so that this definition becomes clearer. To get any truly subquadratic pattern, we start from a collection of graphs from calligraphic P and glue them together by vertices and edges step by step. So first, we take these 2 edges and unify them. Then we take these 2 vertices and unify them. We proceed to glue together these 2 edges, and we proceed with this process as long as we want. And we claim that a pattern H is truly subquadratic if and only if there exists such a stitching procedure that creates H. So in other words, this is exactly the family of patterns that do not contain any of the 3 forbidden induced minors that we talked about before. More formally, for all pattern graphs that do not lie in calligraphic P+, we prove conditional quadratic lower bounds. And for all patterns in calligraphic P+, we present truly subquadratic algorithms and matching lower bounds. Furthermore, the optimal time complexity exponent for pattern H from calligraphic P+ turns out to be just equal to the maximum of the time complexity exponents over all its individual parts from calligraphic P that H is built out of. So for example, in the example from before, it's built out of these parts, and the second part, as we will see later, is the hardest one. So actually the time complexity of the whole pattern is the same as for one such subpart. It means that to specify exponents for all patterns from calligraphic P+, it is sufficient to specify them only for the patterns from calligraphic P, which is done by our main technical theorem. For any P alpha beta gamma times 2 pattern, the problem in question is solvable in time m to the power of 2 minus 1 over f of alpha beta gamma, and this time complexity is optimal under some fine complexity assumptions, where f is defined like this. It is a crazy complicated formula, and obviously I do not expect you to comprehend it right now, and it's not essential for the rest of our talk. This is just some black box that allows us to easily compute the time complexity for the P alpha beta gamma times 2 patterns. Again, I'm sorry for this huge formula, but it's the shortest algebraic representation of f. And also, it could be hard to see right now, but the values of f are always integers. So all the time complexities below quadratic have form m to the power of 2 minus 1 over I for some positive integer I. Notice that as we give both algorithms and matching lower bounds here, this function f encapsulates the true time complexity of these patterns. And it's not just some artifact of our algorithms or analysis. And as I said, it makes it even more surprising that such a result is possible because of this complicated formula. One more thing I would like to point out about this result is that compared to some other modern H-subgraph isomorphism algorithm frameworks, we do not have any logarithmic factors in our time complexity. We are now ready to analyze the time complexity of our example pattern. As we already discussed, it's built out of these parts from calligraphic P. For each of them, we may use the function f to get their time complexities. So for example, this one is solvable in time m to the 2 minus 1/3, this in time m to the 2 minus 1/8, and so on. As 8 is the maximum one of these values, the total time complexity of our initial graph is m to the power of 2 minus 1 over 8. And this is what we wanted. Now that we've stated our main results, let me give you a proof sketch. Let's look at the exponent line. Any number e on this line represents time complexity m to the e. As discussed earlier, we are interested in the portion of this line below 2. And we would like to place all the patterns somewhere on this line. This would be great. Obviously, no graph can fall below 1, as we need to at least read the input. And throughout my explanation, we will be coming back to this picture, and I will use this red segment to represent the portion of the line that we still need to understand. Initially, it covers the whole half-closed interval from 1 to 2, and we will slowly shrink it down. So let's start at the beginning. What patterns are solvable in linear or near linear time? It's widely known that trees are indeed solvable in linear time. It follows from a simple dynamic programming algorithm. So here is the pattern H, here's the host graph G, and for each vertex of G, we find a subtree of smallest weight rooted at it. And we calculate such a dynamic programming table from the bottom upwards. It's easy to see that any forest is also solvable in linear time. As different connected components are independent, we just solve them separately and then sum up the answers. So if we go back to our picture, we can place forests in point 1. As it turns out, forests are actually the only patterns that are solvable in linear time, and let me show you that. If a graph is not a forest, then by definition, it contains a cycle. Let it, for example, be a cycle of length 3. Then we can embed the problem of finding a triangle of minimum weight into this problem. And the minimum weight triangle is a famous problem that is equivalent to the O-pair shortest path, and thus is conjectured to be not solvable in truly subcubic time in terms of the number of vertices in the graph. As the number of edges in a graph is at most n squared, it implies an m to the 1.5 lower bound. If the length of a cycle is more than 3, we can use a more complex embedding of the minimum weight triangle. So we take one part C and we repeat it multiple times and connect only the corresponding vertices with 0 weight edges. Right, we know that if a graph is not a forest, its time complexity exponent immediately jumps to at least 1.5. And thus our search space is now limited to a half-closed interval from 1.5 to 2. If we now go back to our embedding of a triangle into a cycle, it's not hard to see that it can be generalized to an embedding of any induced minor. So if one graph is an induced minor of another one, then the time complexity of the larger one is at least the time complexity of the smaller one. In particular, we may use this idea not only for triangles, but also for cliques of size 4. For example, this graph has a K4 minor, and thus, via a similar hypothesis that minimum weight for a clique cannot be solved faster than n to the 4, we get a quadratic lower bound for this pattern, as n to the 4 is not smaller than m squared. So using this, we may see that if a pattern contains a clique on 4 vertices as a minor, it is already outside of our reach. So we limit our search to graphs that are not forests and do not contain a K4 minor. Let us continue our journey. As we already discussed, a forest is not harder than a tree, as the total answer is equal to the sum of answers of individual connected components. But obviously the same is true for any disconnected pattern. This already tells us that we can focus on connected patterns, but we can go even further. Imagine the pattern is connected, but there is a cut vertex. So there is a vertex, removal of which disconnects the pattern. Then it is pretty clear that the answer on the one side of this cut vertex is pretty independent from the answer on the other side of this cut vertex. We may not, though, just solve them independently, as for example in this case, maybe the optimal vertex to be taken in the upper part is not the same as for the lower part, and then they don't form an H subgraph. But if we would know for each vertex inside this cut part what is the optimal answer to the top and to the bottom, then we would be able to just sum them up. And indeed, the way we solve the problem allows us to do just that. We can go actually even further and use the same argument not only for cut vertices, but for some larger cut sets. Let's define a clique separator in H as some subset C of its vertices that forms a clique in H, and the removal of C disconnects H. For example, an empty set in a disconnected graph is a clique separator of size 0, or a cut vertex is a clique separator of size 1. An edge like this is a clique separator of size 2, and this triangle is a clique separator of size 3. Vaguely speaking, we prove that the time complexity of a pattern H is equal to the maximum of the time complexities over all clique separator free parts of H. So in this case, the pattern consists of 4 different clique separator free parts. This one, this one, this one, and this one. And we can just solve them independently and then somehow combine them into the answer. If we now go back to our exponent line and apply this new tool, we may limit ourselves to only graphs that do not contain clique separators. For example, then, out of forests, only a single edge fits, as other trees have cut vertices. And if we look at the graphs that we are interested in, patterns that are not forests and do not contain a K4 minor, and if we limit ourselves to the ones that do not contain cut points, then they're known as something called series parallel graphs, which is a family of graphs that represent electric circuits. But I will not define what they are, because now we'll limit our desired family even further. To do that, we need to formulate the full power of our lower bound framework that we use. Recall how we embedded a triangle into a clique of length 5, into a cycle of length 5. Here, we just repeated the same part C multiple times. The initial graph had n² edges, and our embedding asymptotically preserved this number. So if the minimum weight triangle cannot be solved faster than n³, then our problem cannot be solved faster than m to the 1.5. We would like to go further with our embeddings and, for example, embed a 4 clique into our cycle. However, how to do that? We should embed the part D somewhere where it would be connected to all A, B, and C, which is not possible for a cycle. But if we allow to put more than one letter per vertex, it becomes possible. It means that now a single vertex of the graph on the left corresponds to a pair of vertices from 2 different parts of the graph on the right. For example, a vertex A and B are embedded here. All we need to take care of is that for each part from the right, it's embedded into a connected collection of parts on the left, so that we can ensure a consistent choice of a vertex from this part. And also that for all pairs of parts from the right, there should be an edge on the left where both of these parts are embedded, so that for each edge of the click, we may embed its weight somewhere. This also has its downsides. Now we have more edges. We have O of n cubed edges, as the ends of some edges have 3 different letters written on them in total. So we need to go through all triplets of vertices on the right to generate the edges on the left. Thus, as finding a minimum weight for click is n to the 4 hard, and we have a cubic number of edges, it gives us a lower bound of m to the 4 thirds, which is worse than m to the 1.5 that we had before. However, if we increase the size of a click even further and try to embed a 5 click, we can still use only a cubic number of edges, but the lower bound becomes n to the 5, so the lower bound for our graph is m to the 5 thirds. And indeed, algorithms working in time m to the 5 thirds are known. And this is the setup for lower bounds that we use. Pick a click of some size and embed it into our pattern graph by trying to maximize the ratio between the size of the click and the maximum number of different letters per edge in the embedding. We call it a click embedding. As I mentioned at the start of the talk, this setup was discovered by Fan, Kutus, and Zhao 2 years ago. And in particular, they showed how to use it to get matching lower bounds for the known algorithms for all cycles. Let me now give you a different example of such a click embedding we will use. Here we embed a 4 click into the pattern graph on the left. You could remember it as one of the 3 forbidden induced minors we had at the beginning of the talk. We embed A and B into single vertices and C and D into 3 vertices each. One can check that it's indeed a valid click embedding. Furthermore, in each edge, exactly 2 distinct letters are embedded. So we still have a quadratic number of edges, which gives us a quadratic lower bound in terms of the number of edges. And uses the machinery that we already have, we may say that if a pattern contains such a graph as an induced minor, its time complexity exponent is at least 2. It turns out that this pattern is an essential part of most serious parallel graphs. And will show that if a serious parallel graph with no cut vertices does not contain this graph as an induced minor, then it's a parallel path graph. So 2 specified vertices connected by a collection of disjoint paths. It means that we're almost done. To get our desired family calligraphic P, it remains to show that at most 2 of these paths may have length at least 3. Sadly, one can show that for this graph, the best lower bound exponent we can hope for using this lower bound framework is 2 minus 1 over 9. However, only a quadratic algorithm is obtainable. And thus, to show hardness of this pattern, we need a different kind of lower bound. To this end, we adapt an idea from Joklikar and Re and use mean plus convolution hypothesis to show hardness. As it turns out, very interestingly, this one pattern for which our click embedding approach failed is ideal for simulating the problem of mean plus convolution verification. I will not get into details of this reduction, but basically we'll use this edge to embed AI, this edge to embed BJ, this to embed minus CK, and the vertices on the sides to make sure that I plus j is equals OK, and then verifying mean plus convolution, so checking whether there are indices I and j such that AI plus bj is smaller than ci plus j, is the same as checking that this graph has a negative weight subgraph of this form. So now, if we go back to our exponent line, we know that our P graph can have at most 2 paths of length at least 3 to be subquadratic. We're almost done, almost there. It remains to see that if such a graph has a path of length 1, then this path is a click separator. This edge is a click separator of size 2. As we already restricted ourselves to only graphs with no clique separators, we can finally say that the graphs of interest for us are exactly P alpha beta gamma times 2 graphs. And indeed, all of them do admit subquadratic algorithms. So we finally arrived to the family we were looking for. Now recall that we not only found a family of subquadratic patterns, but for each one of them found an optimal algorithm and a matching lower bound. From the formula for the value of f, you can imagine that these results are not easy enough for me to present them here. And this is actually the most challenging part of our work that requires a lot of insight. We show some algorithms and that go beyond the classical high degree, low degree approach. And for the first time, we show that this high degree, low degree approach is not sufficient to obtain optimal algorithms for minimal weight H subgraph isomorphism. And from the hardness perspective, we design matching conditional lower bounds based on clique embeddings for all these patterns, P alpha beta gamma times 2. We're now finally ready to build the desired picture of the distribution of patterns between time complexity exponents. To the best of our knowledge, before our work, only the time complexity in point 1 was fully understood. And now we present it for all infinite number of points between 1 and 2 exclusively. As discussed before, all time complexities have form 2 minus 1 over I for some positive integer I. Here, for time complexity 1, we have an edge, then 2 cycles per time complexity exponent, then 1 bipartite clique with 2 vertices per part, then sometimes start popping off P graphs with 1 large path, and then sometimes eventually even 2 long paths, and so on. Let me once again note that these are clique separator free patterns per time complexity, and the whole family for each time complexity is infinite and can be obtained by repeatedly stitching the patterns in the corresponding point and to the left of it via vertices and edges. So for example, as we already know, graphs of exponent 1 are trees, which is stitching edges by vertices and edges. Graphs of exponent 1/2 look more complex. We can use edges, triangles, and quadrangles to stitch them. Here is an example, and so on further for larger time complexities. This stitching that we informally defined at the beginning is exactly the clique separators in the graphs. As subquadratic patterns cannot contain a K4 minor, these cliques should be of size at most 3. And one can show that actually stitching by triangles would not give you anything new, so we only stitch by vertices and edges. To wrap it all up, let me tell you about the future directions this research can go and some problems that stay open. First of all, we understood that we can fully characterize all patterns and their time complexity exponents up to 2. But can we go further? It turns out that as we enter quadratic and superquadratic time complexities, things become much more complicated. But we already tried to go into the direction and discovered that already at m to the 2 plus 1 over 6, we found a pattern for which we were not able to match an algorithm and a lower bound. So it seems like with current techniques, it is the limit of our approach. Thus, closing it would require some novel ideas, either from the lower bounds or from the algorithms. So this also shows us that our characterization up to exponent 2 is close to everything that can be done with currently known techniques. Furthermore, we measured the time complexity in terms of the size of the input, so the number of edges in the graph, but one could also try to measure it in terms of the number of vertices. That would also be interesting to know. Would the same techniques give something interesting or something different is required? I don't know. Moreover, one could be interested in trying to extend these results from graphs to hypergraphs, which would represent relations of multiple parts at the same time from the database perspective. Other variants of the problem could also be analyzed. What happens if we require the pattern to be induced? Our algorithms do not work in that setting, Also, what if the version of the problem is not covered? In this case, in contrast, the same algorithms would work, but there is no guarantee that something faster is not possible. Furthermore, our algorithms and clique-based overbounds work for the combinatorial decision variant of the problem, but the min plus convolution-based overbound does not. And it would be interesting to know whether there is a workaround. And finally, decision and counting variants of the problem are sometimes faster due to the existence of fast matrix multiplication algorithms. But fast matrix multiplication does not always give you an improvement in time complexity. So it would be interesting to know for which kinds of patterns it actually gives a speed up. This is everything that I have for you today. Thank you for your attention.